We'll be looking at some questions now. So our first example is simple but quite eliminating. Okay, so I'm going to write EG1 0 1 divided by 0 tilde 1. That is, I'm going to take x is 0 1 and tilde is the equivalence relation generated by 0 is equivalent to 1. Okay, and then geometry will tell you what this is. We start with an interval and we have the point here which is 0 and the point here which is 1, and we glue them together, and if you think of it physically, it's kind of clear that it gives you the circle. Okay, and so that's what we'll say. Proposition is that x by tilde, which is x bar, is S1, or more specifically is homeomorphic to S1. Okay, so let's see. First of all, we'll define a map to S1. Okay, and remember what we have to do. We can define a map upstairs which is compatible with this relation. So define f bar from x bar to S1 as follows. Okay, so you let f from x, which is 0 1, to S1 be, well, I wanted to go to all of the circle, which, sorry, is so terrible here that I'm going to redraw it, and with assistance. So here's a circle. I want it to be a circle. And here it is a point. So this is going to be the one in the complex plane, or 0 1, which is part of the circle. We define f from 0 1 to S1 be f of t is going to be e to the 2 pi I t. Okay. Then f of 0 equals f of 1. Okay, so this is 0 is equal to 1. Hence, we have f bar mapping. I'm going to write it like this again by 0 tilde 1. This is what I called x bar to S1, such that f bar is composed with q is f. Okay, now at a set level, we see that f bar is a bijection. Why is this a bijection? This is a bijection because f is surjective. That you have to look from the formula. Hence f bar is surjective. So the quotient is always going to be surjective if the image is surjective, because if I have y here and then I have some space x and then I have x bar here and I have a point y and I have a surjective function f, that means I have an inverse image point x. So if I look at its equivalence class, that will f bar of that will be y. So the f bar is surjective. Okay, f is injective. Sorry, f bar is injective as f bar of, if you have two quantities, f bar of x1 equals f bar of x2. Suppose this is true, this implies that f of x1 equals f of x2, which implies that x1 equals x2, or from the properties of the map, it's injective on the interior, or x1, x2 belong to 0, 1. And in the latter case, also we have the classes are equal. So equal points have equal classes. So we see that f bar is a bijection. Okay, now we can unleash the theorem which is useful for compact spaces. So thus f bar is continuous. So it's a continuous bijection from x bar compact. Now why is x bar compact? Because 0 1 is compact and the image of a compact set is compact. Okay, and to a Hausdorff space. Circle is Hausdorff. Hence a homeomorphism. So this is the context in which this result is frequently invoked. That is just understanding the function at a set level. In fact, we invoked two things here. We just understood it at a set level and deduced that at the quotient you were continuous, and then used the fact that you are from a compact to Hausdorff space to deduce that at the quotient level you are actually homeomorphism. Okay, a couple of other examples here. First of all, if I take a square and I identify these two sides, it's described this way. So x is 0, 1 cross 0, 1. And tilde generated by 0 comma y is equivalent to 1 comma y for all y in 0, 1. Okay, then you can see if you glue these together, that's what quotient means, you get a cylinder. Then x by tilde is S1 cross 0, 1 cylinder. Well, why is this? It's very similar to the previous one. As we have here, might as well say proof. Let's define f bar from x by tilde to S1 cross 0, 1 as induced by f mapping 0, 1 cross 0, 1. So I'm just going to say sketch of proof, just only the main idea of the proof. You define this to, so now we are going to take in the first coordinate e to the 2 pi I t. So this is just the domain and domain. We're just seeing the type as 0, 1. And f of xy is going to be e to the 2 pi ix. The first one goes to the circle, but the second one is y itself. This induces a map because 0y is equivalent to 1y generates the equivalence relation, and 0 and 1 in the first coordinate go to the same point, and hence it's continuous. Okay, we see this as a homeomorphism. Actually, we just took the previous examples and looked at products. Okay, and so but you can directly see that, so you have a continuous map because it's well defined, because where the defining equivalence relations go to the same point. It's a continuous because it's induced, and it's from a compact set to a Hausdorff space because this is compact, so its image is compact, and hence is a homeomorphism. Okay, a more famous example, well, cylinder is too common to be famous, is if I glue instead with an equivalence. Okay, so x is this time 0, 1 cross 0, 1. So tilde generated by 0y is equivalent to 1 minus y. So your point here is identified with this point, and indeed if I took the boundary point, it gets identified with the boundary above, not the boundary below. Okay, so then what happened is the quotient is a Mobius bend. The Mobius bend, let me call it some script m. Okay, and this has one boundary component. Observe that, well, let's look at the boundary of this of the square. Observe that this has one boundary component. This is not boundary in the sense of frontier of set topology, but boundary of a surface with boundary, which we won't formally define, but we won't look at manifolds. The point to note is that if I go along the boundary from here to here, okay, so let's start here, right hand to left hand, then the red point is identified with this, and so then we go here and only then come back. So we have an identification between the orange point and the orange point, and the red point and the red point, and as a result we get only a single boundary component. Okay, so that is, let's look at it. Namely, what is a precise mathematical statement? Namely, we have a map from, let's look at the boundary of this, the upper and lower boundaries, the ones that are not identified. 0, 1, so that is where y is, x coordinate goes from 0, 1, but y coordinate is either 0 or 1 to m. Okay, so we have a map from this. So this is 2 intervals. Okay, but what does this induce? So the map, the function 0, 1 cross the pair 0, 1 to m. So m is, remember, 0, 1 cross 0, 1 divided by, I'll just write it as 0y is equivalent to 1 minus y for all y in, of course, the interval. So we look at the interval from the function from this. So here we have 2 intervals, okay, one above the other, but it doesn't matter. This point is identified with this point, and this point is identified with this point. Okay. So we have a function okay. So now consider the equivalence relation on, or even more directly, let's just restrict the equivalence relation. The equivalence relation tilde restricted. So equivalence relation restricted to a subset is an equivalence relation. So restricted to this boundary 0, 1 cross 0, 1, boundary in the geometric sense, is, well, it's generated by, well, suppose this is this guy is 0, 1 cross 0, and this guy is 0, 1 cross 1. Okay, it's generated by the final point of this is equivalent to the initial point of this. Okay, so that is 1, 0 is equivalent to 0, 1, and 1, 1 is equivalent to 0, 0. Okay, but what happens to this? So the quotient of 0, 1 cross this by the, or I won't say off, because the quotient by this, here I mean restricted. What is this? I glued together these 2 points, it became a single interval, and I glued the end together, so it's a circle. And except that you've gone twice around the circle. So when you look at your picture of a Mobius band, the boundary is going to give me, so this guy is identified with a flip. Okay, I could have, maybe I drew it the other way around. So giving you a Mobius bend, a figure that looks roughly like this. It has a twist. It has a single boundary component. So this, you can imagine this being twisted this way as we have it. It has a single boundary component because you go around this and then around this again, which connects up as a single one. 2 intervals glued together gives you a circle, and if you are measuring lengths of length 2 instead of being length 1, and the way you make it a circle is that instead of going at speed 2 pi I, you go at speed pi I, meaning instead of speed 2 pi, you go by speed pi around the circle, so that the first half goes to just the upper half, second half goes to the lower half. This is a Mobius bend. Okay, so we have seen some examples. The final one of this set is a common uh, uh, class of examples. So let me just introduce that notation here. Suppose A is contained in X, is any subset. Okay. And let me actually just make a comment, usually closed or often closed. We'll see why. We'll see an example where it is not closed and where things go wrong. Not right now, later. Right now we'll see a nice example of this. Suppose A is contained in X and it's often assumed to be closed. Can define an equivalence relation tilde A as X is equivalent to Y. These are both points in X. If and only if X equals Y or X and Y are both in A. So we are identifying everything in A to a point. Okay. And then X by A is by definition X divided by this equivalence relation. And our fourth example is, suppose we take Dn and divide it by Sn minus 1, the boundary. Take the disk and D2 for example and add the boundary here. Okay. So then what we get is, actually, if you think of it, you pinch the boundary, take a piece of paper, pinch the boundary, and topologically up to sphere, it's actually going to be Sn. It's an important example. Okay. And this is what we'll see in slightly more detail. Full detail is a bit gory, but let's see some more details of this example. So dn by Sn minus 1 equals Sn plus 1. I'm sorry, Sn, but Sn is contained in Rn plus 1, which just for convenience I'm going to write as x0, x1, xn. Okay, xi in R. And Dn is of course contained in Rn, which is those of norm less than or equal to 1, and Sn minus 1 are those of norm 1. Okay, namely, we define f from Dn to Sn by, well, let's look at D2 here as an example. We'll keep the radial, so the radial direction will go to the 0 coordinate. Okay. By, let's say, f of x1, xn equals, let me just give them names, x0 hat, x1 hat, xn hat. And x0 hat at the origin should go to, let's say, minus 1, and at the boundary will go to 1, or the other way around. Let's send the origin to 1. So where with x0 hat is going to be 1 minus 2 times norm x. Okay. And then what is the norm of the other two, rest of them? Okay, so let me just call that R. So it's the norm of this, and we can write it there. And xi hat is going to be xi up to scaling. And what is the scale? First of all, we'll get rid of the norm of x itself, so that this is on the circle. If this is if xi hat is xi is x, the whole point is not equal to 0, 0, 0, 0, and it's going to be 0 if x equals 0, 0, 0. So just in case one is worried about lack of continuity here, you see if xi is 0, then the norm is 0. Okay, and so you're forced to actually have x0 hat is 1. So you're actually at the origin, you're at the top, you're at the north pole. Okay, so we normal any point other than 0, 0, 0, we first normalize, but then we want it to have the correct scale. And that correct scale is 1 minus 2 norm x, the whole squared. This quantity is so that all of these end up on the unit sphere. And now it is routine to see, so this gives a map Okay, so what happens on the boundary? On the boundary, we can see that 1 minus the entire boundary is mapped to, well, if norm x equals 1, 1 minus 2 norm x equals minus 1. Okay, and so square root of 1 minus 1, the whole squared, so this is 1 minus 1 is 0. So you notice that the entire boundary is mapped to the xi hats are mapped to 0, and this point is mapped to this part is mapped to minus 1. So note, observe f of Sn minus 1, the entire function is going to be equal to 1. Okay, so if I have tilde Sn minus 1, x is tilde Sn minus 1 x prime implies that f of x equals f of x prime. Okay, here it's worth noting, so in general, given f from x to y, we get f bar from x by a to y if and only if f bar of a is a point. Okay, exactly two things are equivalent. Either they're equal, then there's nothing to say, functions are equal, or they're both in A. So then if they're both in A, they must have the same image, which exactly says f bar of A is a point. So indeed here f of Sn minus 1 is f, and f is continuous. That I'm not going to bother to do the epsilon deltonics for these formula. Okay, so observe f is, so we get f bar from dn by Sn minus 1 to Sn, and finally we see this is a homeomorphism, is bijective. Hence a homeomorphism. Why is that? You can see from these formulas that further away points, different points go to different heights except for the actual boundary. I mean, points at a different distance from the origin go to different heights except for the actual boundary. So on the interior, you're still injective in terms of different heights, and the angles are also preserved. So you're injective on the entire interior, and the boundary is all identified to a single point, and so the whole map is injective when you pass to the quotient. It's well defined, it's injective. Surjective because, as I said, the original map is surjective, and so we get a and hence the induced quotient map is surjective. Original space is compact, so we have a compact to Hausdorff space. Hence we have a homeomorphism, and this is a sort of typical example of what we get in geometric topology. We glue things together. In the set topology course, we won't see too many more examples. We'll see a couple, one which will show things are pathological, then projective spaces, which is one large class of examples.